minus R1000 should be quick enough. Let's try that. Hello, it's Jim. Today we are exploring the ROS software stack for RACECAR J, the MIT race car. Now that the software is installed and we can teleoperate the robot, let's take a look at the running system. As background, you should have this book, Programming Robots with ROS, a practical introduction to the robot operating system, by Morgan Quigley, Brian Gerke, and William D. Spart. These are the people that wrote ROS originally, so they should be able to explain it better than I can. Let's put this aside. Let's install some visualization tools. We will also install some plugins. ROS has built-in tools for introspection. We can run those from the command line. We can also use this visualization tool to help us. Let's start up our robot. I've plugged the battery in. Let's start up our game controller. We'll launch this. This is a base RACECAR J. There is no camera or LiDAR installed. When I hold down the button, forward and reverse. And the steering servo works. Let's start up our visualization tool. And let's use a visualization plugin. There are several tools available. Let's use Introspection. This will allow us to look at the running system. We'll get a node graph. We are looking at the nodes and topics. Let's zoom in a little bit here. The makeup of ROS is pretty simple conceptually. There are nodes. The nodes are connected. ROS is a distributed processing environment. A node is a process which performs computation. The environment can be thought of as a graph with nodes and edges. The nodes are ROS nodes. For example, we have the /joy_ node. We can examine this more closely with a command line tool. Let's start one up. Let's switch over to the RACECAR workspace. Source the devil. We can list all of the ROS nodes. So for example, joy_ node. Let's get the information on that. Expand this a little bit. This tells us a little bit more information about the joy_ node. Nodes can talk to each other. There are several mechanisms to do that. One is called a publish-subscribe mechanism. The nodes may subscribe and publish to each other over named topics, which are basically buses. Think of them as the edges of the graph. Joy_ node goes through this topic here, which is a square, /joy, to the JoyTellOp node. We can see that here, /joy is a publisher, so it's publishing out something. Sensor_messages /joy, which is this. And then we have a subscriber /JoyTellOp. So the topic is /joy, /JoyTellOp is the node that is listening. A node can subscribe and publish to multiple topics simultaneously. This topic here, there's a corresponding method to look at ROS topics. We can say ROS topic info /joy. We can see its type. We see its publishers and its subscribers. We can look at the actual messages being passed between nodes. Echo. When we move the joystick, we get values. Basically, Joy node reads what's going on the game controller and converts that into messages in the ROS system. All the different buttons, game controller button, the dead man switch, for example. We can see that when we hold the dead man switch and hit the throttle, the car moves forward. Then the next question usually becomes, how does this get translated into commands which the hardware in the car understands? So let's follow that. Control C to stop our echo. Let's take a look at the form of the message. This is a pretty typical ROS message. Most ROS messages have a timestamp to tell you when they actually happened. They're in this header. And then the actual data for the message. In our case, there are the axes. This is the information that comes out of the joysticks. And then the buttons, which is just an array of the values of the buttons. We can see that that topic goes to the JoyTellOp node. Let's take a look at that one. Now we see that JoyTellOp subscribes to /joy, which was the information from the game controller, and then publishes that information as an Ackermann message, Ackermann drive stamped. In our graph right here, JoyTellOp, we're taking in Joy messages and converting them into Ackermann command mux input teleop. You can think of the Ackermann command mux as a arbitration switchboard. It takes the input and then we'll convert it into a final Ackermann command. In our case, we're taking the teleoperation information, putting it in the command mux, and eventually it will come out as an Ackermann command. We will then send that information to the electronic speed controller on the robot. Let's take a look at the output of the JoyTellOp. It's going to be this topic, which is this. Let's echo that. You can see the type of information that it publishes. It will publish a steering angle, a velocity, a speed, an acceleration, and a jerk. It looks like our speed goes from 0 to 2 when it's going forward. Let's go in reverse. So -2. And our steering angle left is positive 0.35. Right is minus 0.35. Okay, so let's keep following it. So it goes from JoyTellOp into this topic. Then it wanders through this Noblet manager. After the input is arbitrated in the command mux, it will come out as this Ackermann command mux output topic. We can see that it goes to the safety controller node, and then it goes to the Ackermann command topic. So let's take a look at the Ackermann command topic. It comes out of the safety controller and then it goes to the VESC Ackermann to VESC. So let's monitor that for a second with our car running. Same result as previously, pretty much. Most of this is just passed through. And now we're ready to go into the electronic speed controller nodes. So we'll come over here a little bit. And this looks pretty straightforward. It takes the command, goes into this node here. Let's take a look at that node. It basically will publish out the motor speed and the servo position, and it subscribes to Ackermann command, which is basically our Ackermann drive stamped message. And we can see it takes this information and sends it off to the VESC driver for the motor speed and the servo position. Let's take a look at the VESC driver node. You can see the messages start getting more detailed the closer to the hardware you get. This is the VESC driver is basically the code that talks directly to the electronic speed controller. Usually what happens is the closer you are to the hardware, the more information there is available. This is at a much lower level than how we would normally think about controlling the robot. Usually we would just want to say, go left or go right and go fast. Or stop, but go fast. So let's take a look at some of the commands that we would send. So here's one, VESC commands motor speed. When we program the car, we think more about just building up an Ackermann command and sending it through this MUX. And eventually it ends up into the VESC. Once you're into this VESC package, you can think of that as low-level programming. You will want to program the robot using Ackermann commands. So how might you do that programmatically? There is an introspection tool to be able to do that. Let's try to send a command out to the robot. This is the one we want to send. And we need to figure out an appropriate place to insert it. So for now, we'll just throw it in here into the Ackermann command MUX. Let's set our speed to 2 and our steering angle to 0.35. Basically, we say ROS topic, and then we're going to publish it. We are going to publish into Ackermann command MUX input default. Here's the message type we are going to publish. And we do not set up the header or anything, which is this. We set up some of the drive, which is basically the steering angle and the speed. So we say drive, which denotes this part of the message, steering angle 0.35 and speed 2.0. So let's hit carriage return. That wasn't very exciting. Try it again. So that was correct. In our little demo there, our first attempt, you can see that the motor cogged. Cogging is kind of a technical term for it didn't work. This has to do with the way a brushless motor works. You can alleviate that somewhat with a sensored motor. In our second attempt, it worked like it was supposed to, but not probably how you would have expected it to work the first time through. It turns out that ROS is basically running in a loop, and it resets itself at the bottom of the loop. So you send it a command. In our case, basically what happened was we said go forward, and it said okay, and it did that once. It got back to the top of the loop, and then it stopped. So what you need to do is basically insert that into the loop and repeat it. So let's do that. Minus R1000 should be quick enough. Let's try that. You can see that's pretty steady. And if you lower the repeat number too much, let's say from 1000 to 50, you can see that the cogging is much more apparent. That's an introduction to the stack. If you liked the video, subscribe and hit the bell button. Thanks for watching.